All right, let's get started. Sign-in sheet. There. Okay. On the last announcement slide, I'd sort of had this table sort of saying, you know, here's the homework submission deadlines, but we only have one homework left, so there's not really anything to say other than it's due on Friday the 27th. I sent you all an email on Monday. When I wrote the assignment, you know, I don't know if you've looked at Chapter 9, but there's not that many problems in Chapter 9, so I usually like to tweak them a little bit by changing the loads. I forgot to do that on the first submission, so I modified the loads for problem number 2 just to make the problems a little different from year to year. So I've posted that corrected PDF on Blackboard. So I mean, nothing else changed on the assignment. Course evals are online and ready to go. You all know the drill. That what I like to do is I like to have you do them. You can say I'm the worst professor ever. I just want to see that you've done them. And if you complete the survey for the class and you upload an image indicating that you have done the survey for this course, I'll give you 10 bonus points on your homework. So that gets added to the total possible number of homework points that you can accrue throughout the semester. So again, the question is, can you get over 100% on your homework average? And the answer is yes. I've already had a few people do their course eval, and they've uploaded the JPEG showing that they've done it, and when I added the 10 bonus points, their homework average is now over 100, and that's completely fine. So what I've done is the actual course evals, they close Friday at midnight on the 27th, but from what I guess you can still go online and see that you've completed them. So what I'm going to do is just this. I need your uploads by April 30th at 10:15 a.m. because that's when we do our final. So when we have our final, you all take your final, and then I'm going to grade your final and grade and collect all those so that, you know, I'm not going to accept them through the rest of the week because when I get finished with your final, that's it. I'm done with the class. So I figure that's pretty fair. Any questions on that? Again, just if you complete that survey and upload it, let me know. Now, you have to upload it. I have no idea who's done the surveys. All I know is how many people have completed them. Now, just before class, I saw that 3 people had done it. I mean, some others might have completed it in the interim. But I've got, when I checked it, I had 3 people had completed it and 3 people had uploaded permission. And it's happened before where I've had, you know, 27 students do the survey and only 25 of you upload the proof that you did it. And I'm thinking, you could have said I'm the worst professor ever, but just upload the JPEG. That's free homework points, you know. So please tell me, otherwise I'm not going to know. So, because that's confidential. All right. Any questions? All right. Before we get into compression member design and maybe talking about beam columns, depending on where we get on time, I did want to show you this. I was going through the lecture that we did on Monday, and I don't think I was 100% clear on this. So I wanted to clarify. If you recall, when we were doing when we were checking column design details, and we looked at clear bar spacing, we said that this distance had to be a maximum, or could only be a maximum of 6 inches. However, that's only if you have bars that are supported between a tie length. Like if you had a scenario like this where you only had bars tucked into the corners, that would be fine. There is no maximum spacing there. It's only if you have bars supported along the length of a tie. So the reason I ask is, or the reason I say that is if you're doing a, you know, it's very possible that you're working on an exam problem or a homework assignment or just a column design problem in general, and you pick a column that's 20 inches by 20 inches and you need like 4 number 10s, but you check that distance and it's like 13 inches or something. That's completely fine as long as it's tucked into the corners. So I wanted to clarify that. The only time that there's a distance requirement is if you're supporting multiple bars along a tie length, and that's just to make sure that everything is well contained during placement of concrete. Does that sound good? All right, so I just wanted to clarify that. Okay. So let's get into column design because, this is really simple. It's not that complicated. It's probably one of the simplest designs that we will do throughout our reinforced concrete design course, period. Column design is pretty straightforward. So first off, you determine the load on a column. So that's 1.2 dead plus 1.6 live. Let's also clarify something else. Let's make sure we tie this into real world. I want to look at this column right here in the room. So think about this. This column is going to be responsible for the tributary area, what? Halfway over to this column, halfway over to that column, and then halfway over to the adjacent column this way. So if there's some 80 pounds per square foot dead load and 100 pounds per square foot live load, whatever it is, take that pressure load, multiply it by the tributary area for that column. That gives you a dead load, that gives you a live load, factor it to get your PU. Everybody okay with that? I had a feeling by now that that's something that's pretty clear, but I wanted to make sure everybody was okay on that. Now, once you've got your design load, you have to choose a reinforcement ratio for the purposes of design. Now, obviously, you got to choose a value between 0.01 and 0.08. A good starting value, if you're not told, a good starting value is 0.02. That's a pretty nice value for estimation purposes. And then what you do is this. You take that reinforcement ratio and you solve for a required gross area of the column and ultimately required dimensions. Now, what you don't do is take that gross area, multiply it by 0.02 to solve for the required amount of steel. And the reason why is because you're going to, when you solve for your gross area, like let's say you're solving for the diameter of a column, you might solve for the diameter of a column and you might get the required diameter is 17.9 inches. So you say, well, I'm going to round it up to 18. You then take that actual gross area and solve for how much reinforcement you need in that column in order to support that load. One thing that you're also afforded by doing this, what if you do the math and you find that the required diameter is 18.03 inches? There's actually nothing that says you can't round that down to 18 because you're going to use the actual gross area to solve for this. And that's where the difference comes into play. So just make sure that you're cognizant on that. You cannot solve for the required amount of steel by just taking that times that because you're ultimately going to be editing that dimension a bit. So, but that'll become clearer when we do a couple example problems. Check your details once it's all said and done and you've got a column design. Now, unless it's otherwise stated, assume 1.5 inches of cover. That's pretty common for internal elements in a reinforced concrete building. Excuse me. Now, to actually solve for each of these quantities is pretty simple. Yes? Yes, and the reason why is because you're actually going to take the actual gross area once you've solved for what the actual area is going to be and solve for how much steel is required to support that load. Okay? If you were to round down and then say, well, I'm just going to take that rounded down area and multiply it by this, that would be wrong. Okay? So let me sort of say it this way. If you rounded down your area a little bit, what's ultimately going to happen is this value is probably going to go up. It's not going to go from 0.02 to 0.09, but it's going to go up a little bit. So if your concrete area goes down a little bit, your steel area might go up. But again, you got to use a little bit of common sense. I mean, if you solve for a dimension and you get like 18.01 inches, are you really going to say, well, I'm going to round that up to 20 or something? That might be a little overkill. Does that make sense? Remember also, when you solve for a required area of steel, you got to round that up just anyways. Remember, there's only so many multiples of so many bars. So if you solve for a required area of 3.08 square inches of steel, you're probably rounding that up anyways just based off of how many bars there are. Make sense? So it's all about just using a little bit of common sense. So does that sound good? Don't worry. We'll go to that in an example. I think it'll become clearer when we do the calcs here in a second. Now, to solve for so we take it one step at a time. To solve for the gross area, once we've assumed our reinforcement ratio, remember this is just an assumption. We plug and chug, solve for the area, and here's what we get. So maybe another way of thinking of this is this gross area requirement is really just to sort of get you in the ballpark, to just sort of figure out about how big your column size is going to be. I mean, you as the engineer are allowed to tweak this value a little bit because you're going to take the actual gross area and then do another algebraic substitution to figure out what the required steel is. Does that make sense? Everybody okay with that? And don't worry, we've got a couple examples where we're going to clarify that. Speaking of, here's our examples. So, again, I think when we go through this, you're going to go, oh, this actually was pretty simple. So we're going to design two columns. We're going to design a square column and a circular column. Let's design a square column, and I'm making it a point to say it's a square-tied column so that you know what your phi value and your alpha value is. Let's design a square-tied column to support an axial dead load of 130 kips and an axial live load of 180 kips. We're going to begin by using approximately 2% steel, a concrete strength of 4,000, and grade 60, so we know Fy and Fu. I think you're going to find, when it's all said and done, yeah, this actually was pretty simple. Column, well here, let's just do this. All right, so FC prime is 4 KSI. Now Fy, it's grade 60 steel, so what's Fy? There we go. All right, now we're starting off with a rho value, and the way I'm going to write this, I'm going to say it's a rho value of about 0.02. When it's all said and done, that's probably going to change a little bit because of how we round our values and how we select rebar and so on and so forth. That'll probably get tweaked a little bit, but as long as it's between 0.01 and 0.08, we're good. And you do want that value to hug sort of the lower bound. I mean, in the end, usually steel's a little more expensive than concrete, so if you can use more concrete and less steel, that's usually an economical way to go. Now we have a dead load of 130 kips and a live load of 180 kips. Okay? Now, while we're at it, this is a square-tied column, so what's our phi and alpha value going to be? 0.65 and 0.8. So we'll say phi is 0.65 and alpha is 0.80, and I'll put square tied column. So, pretty simple. Okay. So, what's my first step? Say it again. I heard somebody say it. There we go. Can't say, well, it's Monday. It's not Monday. But it's not dead week. You said almost. That was good. Y'all hear it? It's a dead week. You said, when's live week? That was good. Well, it's the week after because that's when we celebrate. All right. So I say factored loads, but it's really just factored load. That's what I said.
Oh, I thought you meant the week after the finals.
No, week of final. Week after dead week. Okay, let's talk about concrete. Okay, so 1.2 dead plus 1.6 live, so that's 1.2 130 kips plus 1.6 times 180 kips, and that's what? Say it again. Or did you say?
444.
I'll say 0.444, right? But 444. Yeah. Do I have a second on that? Okay. All right. So let's solve for our required gross area. Now remember, this really is sort of a ballpark figure because we're going to probably tweak it a little bit. So required AG, okay? Or you can call it AG min. So AG min equals, okay? It's a big fraction. And all this is doing is saying set phi pn equal to pu and solving for the gross area. That's all this is. So on the bottom, phi alpha, and then we have 0.85 fc prime, and that's 1 minus rho g, and then we have plus fy rho g. I don't need parentheses there. So again, this is just taking the capacity of a column, 0.85 fc prime times the area of the concrete, fy times the area of the steel, saying that the steel is just rho times the area of the concrete, doing a little bit of algebra, solving for the area. That's all this is. Okay? So, plug and chug. Okay, so we've got 0.65, 0.8, 0.85, 4 KSI. That's 1 minus 0.02, so I'm going to call that 0.98. Y'all see what I did there? And then 60 KSI, and then that's 0.02. And then that is 444 kips. So the units and everything should work out, right? They're kips and inches. So what does that come out to be? We got a number for me? 137.1? That's not what I got. Say it again. 188.4. That sounds a little better. And I have a second on that. What are the units? Square inches. All right. So that's about how much column we need. That's about how big the column needs to be. Now this is a square column, so how do I determine the side, like how big the side needs to be? Square root of that. So that's going to be different if we're doing a circular column. We don't take the square root because the area of a circular column is not b squared or whatever. So b min is the square root of ag min, and that's what? Have a second on that? Okay. All right. So let's talk a little bit about column dimensions. So more often than not, you like to have your columns to the nearest inch. A lot of times, even the nearest 2 inches tends to be an economical decision because a lot of times, and this is especially true with circular columns, a lot of times you're using pre-built forms that usually come in various increments. So, you probably won't find like a circular column form that's 12 3/4 inches in diameter. You're probably going to say, well, we'll go with 12 or we'll go with 14 or something like that. So if based on this assumption we're needing 13.73 inches, I mean, that's about what we should be using. So what I'm going to do for this problem is I'm going to say, you know what, let's go with a B of 14 inches. Now if this was 14.02 or 0.8 or something like that, I might back it down and say keep it around the 14-inch mark. Again, I'm going to use that actual area and solve for how much steel we would need for the actual column that we're going to use. So we're afforded a little bit of flexibility there. But based on this value, I think it makes sense to go ahead and just use a 14-inch by 14-inch column. So what would the area of a 14 by 14 column be? 196. Now, let's use a little bit of common sense here, okay? What did we assume for our reinforcement ratio? 0.02, okay? Now, based on that 0.02, this is what we got for the area, right? Now, what are we actually using? This. So when we do the design and we go back and check our reinforcement ratio, do you think our actual reinforcement ratio is going to go up or is it going to go down? It's going to go down because we're using more concrete, so that means less steel. Remember what a reinforcement ratio is. It's the amount of steel versus the amount of concrete. If you say, well, I'm going to use a little bit more concrete, that should mean, well, I can back it down on the steel a little bit. That makes sense? As long as you're between 0.01 and 0.08, though, you're golden. Sound good? All right. So now what I'm going to do is I'm going to take this actual value right here, not the 188.4. I'm going to take the actual column size and figure out for this column how much steel do I need. And that's where you get the freedom to tweak it a little bit. So required AST. Okay. So the required area of steel for the column is, so AST minimum equals phi alpha, oh, sorry, that's wrong. Fy minus 0.85 FC prime. And then on the top, I think I went a little overboard on that line there. Pu minus phi alpha 0.85 FC prime Ag. Now before I move on, are you all okay with these equations? Because I don't want you to feel like they're coming just out of the clear blue sky. Okay? Because all I'm doing with these equations is this. Like for this one, this right here, this AST min. All I'm doing is I'm taking this equation and I'm setting it equal to Pu and I'm solving for that. So take this equation, set that, Pu equals all this and solve for AST. Just do a little bit of algebra and simplifying it, and that's what you're going to get. So I don't want you to think there's any magic behind these equations. There's really not. It's just a little bit of algebra. Okay? Everybody okay with that? All right. So equals, okay, so let's plug and chug. So 444 kips minus 0.65. Now watch this. I want you to pay attention here, okay? So 0.65, 0.8, 0.85, 4 KSI, but then Ag, I'm not using the 188.4, I'm using the actual area, 196. And then down on the bottom, 0.65, 0.80, and then we'll say 60 KSI. Actually, I need a bracket there. So what does that come out to be? 3.12? I got 3.31. Check your parentheses. Probably on the bottom. Because this quantity here is in parentheses right here. Getting 3.31? Okay. Now, does anybody have an option that'll work for this? First off, where would you go? You could use that beam design chart. Let me see that. Thank you. Remember this beam design chart? Maybe I should put beam and column design chart because you can use this table to figure out multiples. Now, are you going to use 7 bars? 7, I'm not saying number 7 size. I'm talking about like 5 bars or 7 bars. No, you're going to try to keep it equal. Like 4 bars, 6 bars, 8 bars. Anybody got an option? Let's see what you got. 3.31. You got 4 number 9s. Okay, 4 number 9s will work. Don't use 5 bars. 6 number 7s, what's the area there?
3.61.
3.61. We can probably do a little better.
Do 8 number 6s.
How about 8 number 6s? Y'all good? What's the area on 30 number 3s? Okay. 1 number 18. There we go. Just 1 number 18. Show 8 number 6s. Now, what's the area of that going to be? 3.53. So, again, you got to consider you're taking that, column size and you're knocking it down or up a little bit, but once you've got your actual column size figured out, you're taking that actual column size and you're figuring out how much steel do you need for that, and then you're still bumping it up a little bit. So I don't want you to think you can't round this down a bit or round it up. You've got a little bit of freedom because once you figure that out, you're solving for that directly, and then you're still rounding up. So. No, you would have to tie it to something because how do you, think you're going to have a number 18 bar that's 20 foot tall that's just standing there.
That could be your call. Yeah.
We're saying that this is the same for like
Have you ever worked with rebar? With I'm serious. Have you ever done a driveway or done, something in your back porch or something? Have you ever seen a number 18 bar? Now, imagine manipulating number 18 bars on a simple building site. Just getting them around and manipulating them. They're huge. They're absolutely massive. I'm saying bluestone dam. That's different. That's a huge, complicated structure where you really need it. In other words, use it when you need it. You don't need it. You can get by with number 6s. And also, think about availability. This is a reasonable point to bring up, but also, just go to a supply yard. You're going to find number 6s any day of the week. But number 18s, are they going to have enough for your entire building any day of the week? That's a gamble.
But this is America. Bigger is better.
It's a joke I tell in steel design. I say the number 14 by 800, it'll work. Every time, I promise. It will work. Are you talking about for spirals? Well, you're talking about the longitudinal reinforcement, or the transverse reinforcement, the stuff going around, not the bars that are going up and down. The bars up and down really aren't going to do that. No, you'd have something there. You'd have to have something holding it up. You would, probably what you would have is, you'd probably have, if you wanted to go this way, what was that? So here's your form. There's a couple ways that you could go about it. Depending upon the column size, you could have, maybe 1 or 2, or here, let me put this here. You could have, let's say, 1 rebar chair, 1 rebar chair and 1 rebar chair here holding that, 1 bar right in the middle, and just have that space every so often. But good luck finding a rebar chair that's that deep. You're talking about 1 rebar chair that would have to be 8, 10 inches deep. So that probably wouldn't happen. So probably what you would do, in all honesty, is you'd have 1 tie going around it, and you'd have rebar chairs holding that in place. And then you'd have to have another loop tying those, and then tie your rebar to that. So you'd have a lot more going on just for that 1 bar than you'd think. You got to keep it there, And think if that falls over, that's a number 18 bar that's about like that. That would hurt a lot.
Do we ever have to worry about the development plan or column?
That's a good question. Do you ever have to worry about development length on a column? You do. There is a model to compute the compression or the development length of elements in compression. We didn't cover it because in the grand scheme of things, it's usually not as big of a deal as elements in tension. The development length is usually pretty short comparatively. It's tension that's the problem. So, but it is there. I mean, your textbook even lists it, but it's a lot like the other development length models. It's just plug and chug. It's the same factors, just plug and chug. Good question. Sound good? We're not quite done with this problem because we've got tie spacing, tie selection to do. So, has everybody got this? Okay, I'm going to move on to the next one. Or the next part of this problem. Now, tie selection and spacing. First off, the longitudinal bars that we picked are smaller than a number 10. So, in other words, the actual ties that I'm going to use, it's common to either use a number 3 or a number 4. Because we're dealing with smaller bars, I'll say longitudinal bars smaller than number 10s, use number 3 ties. Okay? So I think we've already got a lot of decisions made. We know that the column is going to be 14 by 14. We know we're going to use 8 number 6s, and we know that we're using number 3 ties. Now, as for spacing those ties out, you're the designer. More ties means more steel, means more money. So do you want to use the most amount of ties possible or the least amount of ties possible? Least amount of ties possible means you care about minimum spacing or maximum spacing? Maximum. You want to space them out as far as you can. So let's check max tie spacing. Now, does anybody remember how you check max tie spacing? Remember, there's 3 values. What's that? Well, we're not there yet. We're going to get there here in a sec. But I'm talking about how far apart the ties are spaced. I'll give you a hint. The first one was 48 tie bar diameters. So that's 48 times, what's the diameter of a tie bar on this one? No, tie bar. Is everybody with me? I feel like everybody's like, what? Okay. We did this in a previous example, but if you recall, we had to check the minimum and maximum tie bar spacing. So we had 48 tie bar diameters. We had...
Is that always 48?
Yes, these limits are the same. I just showed it, but what's the next one? 16 longitudinal bar diameters. So 16 times, now what's the diameter of the longitudinal bars? What size bars are we using, guys? And what's the diameter of a number 6? Somebody else, back here. Now, hold on, no. For anything up to a number 8, how do you find the diameter? 6 over 8, so 3/4. Now, if it's over, then if it's a number 9, number 10, number 11, you got to look it up. And then, what's the third one? The least column dimension. So this column is 14 by 14, so that's just going to be 14 inches. So we've got 14 inches here. This top one, 48 times 3/8, this is 12? This is 18, and this is 12, right? So I propose that, well, let's check there's 2 other limits that we've got to check. So first off, we can use number 3 ties at what spacing? 12 inches. So there's 2 other limits that we've got to check. So I'll put remaining limits. The first is row G, because we assumed a value of 0.02, but we upped our areas and changed all that around, so we just need to go ahead and check that. So that's AST over AG. So what is AST? 3.53, the actual area. So 3.53 square inches. And what is AG? 196. It's not the 188.4, it's the 196. Okay, and what does that come out to be? 0.018. So when it was all said and done, that changed a little bit because we changed our column size and we changed we had to up the rebar and what have you. But in the end, that's okay, right? Okay. Now, let's see if we can do this in our head. Clear bar spacing. Now remember, clear bar spacing, we're using 8 bars, so we do have that 6-inch limit. So what do we got? We've got 14 inches. Tell me what to do. We subtract what? 2 times the cover. We'll use 1.5 inches. Then subtract what? Well, now hold on. Don't worry about the bars yet. There's something else we got to subtract. 2 what? 2 tie bar diameters. Are y'all with me or? Okay, so 2 3/8 of an inch minus. Now, how many longitudinal bars are we going to subtract? Think, if you've got 8 bars around the column, how many are you going to subtract one way? 3, right? But we're talking about this. We're talking about this situation right here. This is what we're talking about. So we have the column, right? We do 2 covers, 2 ties, and then 1, 2, 3 longitudinal bars, and then what do? Divide the whole thing by 2. So So 2 times 3/4, and that's 3. And we divide the whole thing by 2. So what does that come out to be? 4 what? 4 inches. Is that good? It's got to be under 6. So therefore, here's our column. So we got 14 inches, 14 inches, 1.5 inch cover. We've got number 3s at 12 inches, and we have 8 number 6s longitudinal rebar. What do you think? I mean, is that really that hard? Yes. Well, that's true, but I think my response is don't guess a row of 0.01. Like just don't do that, because you're setting yourself up for more iteration. Because if you do that, you are right that you could have an actual row that violates the limit, and then you've got to change stuff again. That's why, just for ease and just rule of thumb, like if you've been doing this for 30 years, you'll learn don't guess 0.01. Guess a little bit higher to give yourself a little bit of wiggle room. Exactly. Exactly. What do you think? Isn't that bad, right? This is pretty simple. Let's see if we can knock out some on our remaining column design example. This one isn't that bad, okay? So you understand this? All right. Then let's look at the next example. So, hold on. Okay. So we just did this column. Now we're going to do this one. So what really changed, the only thing that changed is two things. Now, I mean, our actual problem is going to change a little bit, but the only two things that changed from a problem description are, instead of doing a square tied column, we're doing a round or a circular spirally reinforced column. Now, that's going to do two things to our computations. The first thing it's going to do is it's going to change how we actually solve for the column's dimensions, because the area isn't b squared, it's pi over 4, b squared. So we're going to have to change that. But what's the second thing it's going to do to our computations? Because it's round and it's spirally reinforced. Alpha and phi are going to change. That's going to change that as well. And there's a little trick on the steel, or there's a little note on the steel thing I need to bring up when we get there. Second thing is that our loads changed for this problem, so that's no big deal. Okay, all right. What happened here? Oh, there we go. Got all tangled up. Okay, so 19b, again, we've got FC prime is 4 KSI. We've got FY is 60 KSI. We've got a rho value. Again, we're going to assume a rho value of about 0.02. I didn't do that. That just happened. We've got a dead load. I didn't do that either. A dead load of 240. What is happening with this pen? Is it 300? 300 kips. Okay. So, what's one other? We also know our phi value is 0.75, and our alpha is what? 8.5. There we go. Circular and spiral. Okay. So, same process as before. We start off with a factored load. So what do we got here? $768. Do I have a second on that? 768. Why did I write 7? I do, but I have the answers, but I know how to do this. I'm trying to make sure you all know how to do this. And what if I'm wrong? I'm not, but what if I am? All right. So, phi, alpha, so that is, and again, make sure you get your parentheses right. So that's 0.75, 0.85, then brackets, so 0.85, 4 KSI, and then that's 0.98 plus 60 KSI times 0.02. And then that load is 768 kips. We usually spec columns based on their diameter. So, I mean, an 18-inch diameter column is the same thing as a 9-inch radius column, but we usually spec based off diameter. What are we getting here? I got 265.8 inches squared. Do I have a second on that? Okay, so this is a circle. How do I determine the diameter? What do I do? All right, so if the area is pi d squared over 4, so 4 area over pi is d squared. Therefore, the diameter, the minimum diameter, is 4 AG min over pi. Everybody okay with that? So 4 times 265.8 square inches over pi. .4 inches. Okay, so we've got a little bit of a conundrum here. What do you think? Do we round this, circular columns, they tend to be spec'd out every 2 inches. Do we round this up to 20, or do we just go with 18? I say let's go with 18. Now that's going to result in a little bit more steel, but we've got the wiggle room. We're only using a row value for design of 0.02. We got plenty of space. So I say use an 18-inch diameter column. So what would the gross area of the actual column be? It's going to be less than this. A little bit less. 254.5 square inches. All right, we're going to do the AST calc and then we'll call it. So, therefore, required AST, so AST minimum equals phi alpha Fy minus 0.85 Fc prime, and then Pu minus phi alpha 0.85 Fc prime Ag. Now I want everybody to watch this up here because I want you to see that this isn't a mistake, that this isn't a typo. Watch this. Okay? Watch the top part of the fraction. So what do we got? Pu is 768, right? Now watch this. Minus phi of 0.75. Alpha is 0.85. But then I also have another 0.85. So that 0.85 shows up twice. That's not a mistake. That's supposed to be there. So 4 KSI and then 254.5 square inches. So I wanted you to see, like those 2.85s, they're supposed to be there. So on the bottom, 0.75, 0.85. Fy is 60 KSI minus 0.85, 4 KSI. That was sort of the last thing I wanted to show you, is that those 2.85s, that's not a typo.
6.
Say it again.
6.
So I think if you track it out, it actually comes out to 5.997. So kind of funny how that one worked out, isn't it? It's like I meant for that to happen or something. Would I ever do that?
You're
No, that's a great point. You can use 7 bars on a circular column or something like that because it's not really a symmetry issue. Just space them out evenly and call it. Yeah, great point. We'll finish this one out on Friday because we still got spiral reinforcement to do. And then we got to talk about beam column interactions. So that's all I got. I will see you all on Friday.